Hi all. Sorry I'm late this morning. I was having some connection issues to get into Zoom, but looks like I have been able to, so that's good. So again, my apologies for that.
Good morning, Professor.
Good morning.
And thank you for acknowledging that you can hear me. That's good. I appreciate that. All right. Let's get started. We're going to start on Module 9 today. So at this point, we have been through Module 7 and 8, so there should be no reason that anybody shouldn't be able to at least get a start on those. Module 9 is going to be about stoichiometry. And, the main thing, it's not incredibly difficult. The main thing that people really have trouble with is the percent yield and limiting reagent. And we'll get to those, and that'll be what I'll mainly focus on, I think, today. Now, when we're doing stoichiometry, what we're talking about, of course, is mole ratios or mole-mole relationships. All right, hopefully, I know, it doesn't look like I'm sharing here. Okay, now I am. Something's in chat. Oh, okay. Okay. Now, when we're talking about mole-mole relationships, oh, geez, come on. I usually like to see if we can get this going here. There we go. Now we're in business. Oh, no, technology's not my friend today. Okay. Yeah, something's really wrong with my, I'm going to have to restart something here. Give me a second.
Yeah, no problem. Good luck, Professor.
Yeah, good luck is right. I'm going to need it. All right, this looks like it might be better now. Maybe not. This is not behaving the way it should. I'm going to stop sharing for a second. Let me go into another profile here and shut down some stuff that might be causing issues. Okay, let's see if this is going to be behaving itself now. That's better. Okay. All right, you all can still hear me, correct?
Yeah.
Yes, Professor.
Thank you.
Again, yes.
So when we're doing these kinds of stoichiometry problems, I like to use this kind of modified flowchart where we have QA goes to mole A, goes to mole B, goes to QB. Because when we're talking about stoichiometry, it's always 1 mole of something to 1 mole of something else, or X moles of something to X moles of something else. That's always the central part of the stoichiometry situation. Now, when I say QA, what I'm usually talking about here is grams of A or liters of A, and that's going to be at STP. Well, let's be a bit more specific than that, gas at STP. And for QB, again, it could be grams of B or it could be liters of B, gas at STP. And I think if you're just aware of this kind of flowchart or even vaguely aware of it, then it makes the dimensional analysis required to get answers for these kinds of problems fairly easy. So if we take something fairly simplistic here, how many moles of HNO3 are required to form 6.5 moles of H2O? What I can tell you is that words like required to form and those kinds of things, they're just really words that don't mean a great deal to the actual solving of the problem. The focus should be on whatever has the number in front of it. That's where I would start with my dimensional analysis. In this case, it'd be 6.5 moles and it'd be H2O. That's what we have. And what we're looking for is moles of HNO3. So if you look at the flow chart, we're starting at this point where I've got the cursor, moles of H2O, and we're going to moles of HNO3. So we're not even worrying about QA and QB in this instance. So it's just a one-step process. And I know that moles of H2O will go on the bottom and moles of HNO3 will go on top. So what's the relationship between these? Because if you'll remember when I was talking about module 7, I was saying when you see this line, you verse it or you word it as for every. So moles of HNO3 for every mole of H2O. So what do we mean by that? Well, whenever you're given a stoichiometry problem, you're also given an equation. A balanced equation, by the way, is something you don't have to balance. And you can see the relationship between moles of H2O and moles of HNO3. There's going to be 8 moles of HNO3 and 4 moles of H2O. That's the relationship. And these are exact numbers because they come from coefficients for an equation. And if we were to complete this, then this would be just 13 moles of HNO3. Now this makes sense because if you look at the equation, you've got double the number of moles of HNO3 for the number of moles of H2O formed. So if we're starting out with 6.5, so if we're actually getting 6.5 moles of H2O, we must have started with 13 moles of HNO3. So it makes a lot of sense, I think. Does anybody have any questions so far? So what you should have gotten so far is that when we're dealing with mole relationships, then we're using the coefficients in a balanced equation that's coming along with the problem. And there always will be one of those. All right, let's see if I can get a bit more luck with this mouse on another surface. Yeah, it's better. All right. I think I'm getting the hang of this technology stuff today. It didn't start out very well, but I think it's coming good. All right, let's look at, do anybody have any questions? Other questions about this? Okay. So let's look at this one. We've got how many grams of S would be formed if 4.25 moles of HNO3 were consumed. Again, just ignore the formed and consumed. It really doesn't matter that much. But we are starting out with 4.25 moles of HNO3. I can see that in the problem. So whatever has a number in front, that's what you're starting with. Now, where are we going? Well, we're going to grams of S. That means it's a quantity over here. And we do have to go through moles of S in order to get there. So we know times and then times in order to get to where we need to get. We know it's moles HNO3 on the bottom here to cancel what we have on top. The next thing we have here is moles of S. And down the bottom here to cancel that, we'll have moles of S. And then because we need grams of S, that's what goes on top. Now, one thing about this flowchart, and this is really the one thing I really want you to take note of here. If this is moles of HNO3, this is moles of S, this is grams of S. You can see that everything you want at each step is always, in the flowchart, is always going to be on the top line of your dimensional analysis. Moles HNO3, moles of S, grams of S. Moles HNO3, mole of S, grams of S. All of that will always be on top. And if you know that, then you always know what goes on the bottom, because whatever goes on the bottom in the next step is there to cancel whatever you put on the top in the previous step. So you've already got a blueprint here for exactly what goes on the top line of your dimensional analysis. And because you know what goes on the top line, then you know what goes on the bottom line. I hope that's clear to everybody. Does anybody have any questions? I'm not hearing anything. Are you sure? Now, one thing you'll notice is I didn't put any numbers in. All I've done is put in units, because that's how you generally handle dimensional analysis. Units are king, so I deal with the units first, and then I put the numbers in later. So when we're looking at a relationship between moles of S and moles of HNO3, we go back again to the equation we're given, and you can see the relationship is 8 moles of HNO3, 3 moles of S. So 8 and 3. And again, I'm just picking these up directly from the coefficients in the equation. And then we need a relationship between grams of S and moles of S. Do you remember this line? It means for every. So how many grams of S for every mole of S? That's what we're looking at. That's the molecular weight. 32.07, I believe, grams of sulfur over 1 mole. That's for 1 mole. So this is where sometimes people get confused. They say, well, hang on, we know everything has to cancel. Yeah, the units have to cancel. But what they'll sometimes do is they'll say, well, that's 3 moles. Shouldn't this be 3 moles down here? The answer is absolutely not. Because remember, each of these is taken separately as an equality relationship. So 3 moles of S is related to, or is for every 8 moles of HNO3. We get that from the reaction. It's 32.07 grams of S for every 1 mole of S, not every 3 moles of S. You have to take them separately. Okay, I have a question in chat here. Okay. Does anybody have any questions at this point?
Why does that have to be separately?
Because these lines here are equality relationships in and of themselves. 32.07 grams of sulfur for every 1 mole of S, not every 3 moles of S. 1 mole of S is 32.07 grams, not 3 moles. Do you see what I'm saying?
Yeah.
This is why you've got to take everything separately. But Michael, you need to understand the entire process and understand the relationship between my modified flowchart and the dimensional analysis. That the top line represents the top line. So the line in the flowchart represents the top line of your dimensional analysis, and the units will always cancel. Not the numbers, the units will always cancel. Do you see what I'm saying? That's what I'm trying to get at.
Yeah, thank you.
Okay. Does anybody have any other questions? Well, let's talk about Sig Figs. The Sig Figs, again, will be determined generally by the starting, well, actually in Model 9, pretty much always, by what you're starting with. So we're expecting 3 Sig Figs at the end. And the answer there would come out to be 51.1 grams of sulfur. Does anybody have any questions?
I might have missed this, but why are we looking for grams of sulfur if it's not an HNO3?
Well, do you see how we've got, well, we've got Haley, we've got a couple of things going on here. We've got a reaction, and the question is this: how many grams of sulfur would be formed if 4.25 moles of HNO3 were consumed? So this is a reaction, and we're using up HNO3 on the reactant side. We're forming sulfur on the product side. That's where the sulfur is coming from.
Okay, thank
Because
you.
the HNO3 is reacting. Is that sufficient for you?
Yeah.
Okay. See, we're dealing with a different kind of process than what we were dealing with in Module 7. In Module 7, we were pretty much dealing with compounds or sometimes atoms within those compounds, but never were we dealing with actual chemical reactions. Stoichiometry is strictly about chemical reactions and mole-mole relationships. All right, does anybody have any other questions so far about this? Sometimes I do get comments about this that, once they see, and some people have never seen it really presented this way before with this modified flowchart. And often the feedback I get, generally speaking, is pretty positive. People say that, oh, okay, I didn't realize it was actually this easy. That's hopefully where I want you to get to. If you're not really feeling that way, then you've got to ask some questions to get you to a point where you can eventually be able to say that. For others of you, you've seen it presented this way before because you've had me in the past or whatever, but many of you haven't. Let's see. I don't think I'll do that one. Okay. Now, what about something like this? How many moles of HNO3 would be reacted with 24.5 grams of Bi2S3? So where do we start? Well, that's pretty easy. You look at whatever has the number in front of it. That's where we're going to start. Right. Then you look at the flowchart and you say, well, where do I have to go? Well, where are we starting? Well, we're starting at Q of A, quantity grams over here, not moles, grams. And we're going to here moles of HNO3. If you look at the problem, that's where we're going. Now it's going to require 2 steps. So if you remember what I told you, you've got grams of Bi2S3 here. That'll be moles. A is Bi2S3, what we're starting with. Moles of Bi2S3 is what's going to go on top here. And what's going to go on top here will be, of course, be moles of HNO3, which is what we're looking for. So what goes on the bottom? Well, it's easy. It's just whatever's on top in the previous step. See, notice I'm not putting any numbers. It's so much easier if you do it this way. What's the relationship between moles and grams? So it's 1 mole, and I think it's 514.14. I'm going to check this. Yeah, 514.14. grams of Bi2S3. So 1 mole is that. So Michael, you were asking before about, why they have to be separate. Well, it's because they're separate relationships. 1 mole of Bi2S3 is that many grams of Bi2S3. HNO3 and Bi2S3 moles and moles. Well, we look back at the reaction now again. And for a relationship there is 8 moles and 1 mole. So 8 moles of HNO3, 1 mole of Bi2S3. And that'll allow us to come up with our answer, which will be 3 significant figures again, which would be 0.381 moles of HNO3. Remember, the leading 0 is not significant, never is. Does anybody have any questions? All right. Well, let's look at the next kind of problem here, which is going to use the entire flowchart. And that is how many grams of sulfur would be formed if 20.25 grams of Bi2S3 were consumed. Okay. So you can see this is just an extension of what we've been working with. So 20.25 grams of Bi2S3. So where are we starting in the flowchart? We're starting here at grams. Where are we going? We're going to grams of sulfur, which is going to be over here on the other side. I'm going to stop there. Is anybody having a hard time knowing how to use the flowchart in conjunction with the problem when I tell you that where we're starting, where we're going in the flowchart? Is anybody having trouble with that?
Not really.
No.
Okay. So in order to get there, we know we're going to need 3 steps. I don't have sufficient real estate here to do it in one line, but you'll get the idea of what I'm doing. So we've got grams of Bi2S3, if that's what we're starting. Look at the flow chart. What's next? Moles of Bi2S3. Moles are the same thing. Then what are we looking for? Moles of B. What are we looking for? We're looking for sulfur. So moles of sulfur will be next. See? Grams of Bi2S3, moles of Bi2S3, moles of sulfur. What are we after? Grams of sulfur. So there you go, the whole top line, right, is already here from the flowchart. I'm going to stop here. Did anybody have any problems with what I just did?
No.
Okay. So what goes on the bottom? Well, whatever's on top in the previous line. Grams of Bi2S3 goes under moles of Bi2S3. Moles of sulfur, that'll be moles of Bi2S3 on the bottom. Moles of sulfur is going to be on the bottom here. So whatever's on top in the previous line, that's the unit that goes on the bottom. Then we look at the relationships. 1 mole is 514.14 grams of Bi2S3. That's the molecular weight. Moles of sulfur to moles of Bi2S3. Here we go. 8 moles of Bi2S3. 1 mole of Bi2S3, 3 moles of sulfur. Okay, 3 moles sulfur, 1 mole Bi2S3. And the last one, 32.07 grams of sulfur, 1 mole of sulfur. That's what goes here. So then we go ahead, we do the math. That's got 4 sig figs. Our answer comes out to be 4 sig figs, and it would end up being 3.788 grams of sulfur. Does anybody have any questions at all?
So do you have an example of when the sig figs won't match up?
Not really.
Sig figs, okay, 'cause sig figs are always like my weakest thing.
In this instance, for module 9, it's actually fairly easy, Joseph, because I'm almost 100% sure, I'll say 99% sure, that all you have to do is look at the beginning, and that will tell you how many sig figs you'll need at the end.
Okay, thank you.
Now, the reason for that is because if you look at the molecular weights, you'll see that 5 sig figs, you'll see 4 sig figs down here. They're never less than 4 or 5 sig figs. And then you've got this 3 and this 1, which are counting numbers, which come from the reaction equation, and those are never included in significant figures.
Thank you.
Okay. Anybody have any other questions so far? Okay, we'll do one more example here. I like this one here. How many liters of NO gas at STP would be formed along with 205 grams of sulfur? Okay, so I wanted to throw something in here about the gases at STP. Okay, so again, 205 grams of sulfur, that's where we're starting. And then where are we going? Well, we're going to liters of NO gas. So in order to do that, we're going to put grams of sulfur, moles of NO over to liters of NO. So we do know that we're going to be doing three steps again here. So we'll have on the next one moles of sulfur, then moles of NO, and then liters of NO. Any questions so far? So units on the bottom, grams of sulfur on the bottom of a mole of S, moles of sulfur on the bottom of moles of NO, and then moles of NO on the bottom of liters of NO. Any questions? Okay, now the relationship, 1 mole of sulfur, 32.07 grams of sulfur, molecular weight. Moles of NO to moles of S, again, we look at the reaction equation and you can see that it's 2 moles of NO and 3 moles of sulfur. So 2 moles of NO, 3 moles of sulfur. See, it's that easy. You just look at the coefficients, you put those numbers in front. And then now the relationship between liters and moles of liters of gas at STP, 22.414 and 1 mole. We looked at this last time when we were dealing with module 7, when we were talking about the relationship between liters of gas at STP and moles, and it's 22.414 liters for 1 mole. And again, that line means for every. Does anybody have any questions? So at this point, let me talk about how you would put this into your calculator. And I'm just going to show you this is how I would put it into my calculator. It doesn't matter what calculator I'd have. This is how I would do it. I would do 205 times 2 times 22.414. So everything across the top I've multiplied, ignored the ones, of course. They don't really have an effect here. Then I do divided by 32.07 and divided by 3. And that'll give me the right answer every time. So what did I do there? Well, I multiplied all across the top, and then I divided anything that was on the bottom. And you'll notice I can just go times, times, divide, divide. And that way I don't have to handle everything separately. I can just do it in one big, long, crazy step. Does anybody have any questions?
Which calculation do you think will be better?
Could you repeat that, please?
Which calculation? What do you think is going to be better?
I'm not really understanding your question, Michael.
Like, which calculation is going to be easier? Like, is it multiplying and then dividing? Like,
just what you see what I did just now on the bottom here? That's the easiest thing you can do. The concept is just multiply everything across the top. All the numbers are on top, and then divide by anything that's on the bottom.
Thank you.
All right, that's all you have to do. Yes, Joseph.
For the second line fraction, whatever, how did you get 2 moles of NO and 3 moles of S to equal each other?
Okay, look at
up there top. I forgot to look at the top. Sorry. Nope, never mind.
Okay. Remember, with all of these stoichiometry type situations, you're always given a chemical reaction, Joseph, every single time. And what's more, it's always going to be balanced already for you. All right, any other questions? Any other questions? Okay. Oh, and by the way, the Sig Figs on this one, 3, so it comes out to, in this case, to be 95.5 liters of NO. Okay, let's take a look at our friend, the percent yield problem. So this is one that tends to give people fits. It really shouldn't, but it does. And part of the reason is because it looks complicated and there are 2 things with numbers in front of them. So it can be difficult to know where to start. So let's first of all talk about exactly what a percent yield is dealing with. Well, what happens is when we're doing chemical reactions, we usually don't get everything we hoped to get. It's kind of like life, really. You know, you have hopes, you have expectations, and sometimes they're just not met. Well, actually, in the case of reactions, they're never met. There's always going to be a situation where you're never going to get back as much product or get as much product as you hope you would get from the amount of reactant you're using. That's what we're always doing. So we're always starting out with A, and we're going to something else B, and we're always starting out with an amount or a quantity of A. And what we're trying to do is get a quantity of B. So, you know, but how much are we supposed to be getting here? And the thing is that we always get back less than what we had hoped to get, theoretically. So what we're going to do here is determine, well, how do we get a theoretical yield, how much we're supposed to get? And then how much we actually got is given to us in the problem. So if you look at the wording here, what is the percent yield of sulfur? Well, look at what sulfur is here. Sulfur's a product. What's the percent yield of sulfur? We're always being asked about a product when we're asking about percent yield. If 100.0 grams of Bi2S3, that's a reactant, is reacted to form 10.0 grams of sulfur. So we actually get 10.0 grams of sulfur, but you can be assured that that 10.0 grams is less than what we expected to get. So we have to figure out how much sulfur we were expecting to get. And that's what the theoretical yield is about. Does anybody have any questions so far? So what's the secret with the percent yield problems? It is always start with the reactant. Because in a percent yield problem, you're always given a reactant and a product. Is anybody uncertain about what I mean by reactants and products when looking at a chemical equation? Okay, reactants are always what we're starting with, products are always what we're finishing with. But with a percent yield problem, we always start with the reactant. So when you're looking at this problem, you can say we've got Bi2S3, we've got sulfur. That's what we're starting with, is the reactant Bi2S3. So that's what I do, 100.0 grams of Bi2S3. That's where we're starting. What are we looking for? Well, we're told we're getting 10.0 grams of sulfur. So we need to have apples to apples, oranges to oranges. So we know that that's what we're looking for, is grams of sulfur. So that's where I'm going to go. I need a 3-step process to get to that point. Excuse me, sorry. Oh,
Bless you.
thank you.
Bless.
So grams of sulfur is what we're looking for at the end here. That's why I've put it at the end. So what goes in between? Well, according to the flow chart, we're starting with grams of Bi2S3. This will be moles of Bi2S3 here. Notice again, I'm not putting any numbers in front. That'll be moles of sulfur here. And then on the bottom, we'll have grams of Bi2S3. It will have on the bottom here, moles of Bi2S3 to match what we have on top. And then moles of sulfur goes on the bottom. So again, we handle these separately. 1 mole is by 14.14 grams of Bi2S3. The relationship between moles of sulfur and Bi2S3 is 3 moles of sulfur, 1 mole Bi2S3, and 32.07 grams of sulfur to 1 mole of sulfur. So when we do the math on that, what we end up with here is 18.71 grams of sulfur. So what does that number represent? Well, it represents the amount of sulfur we should have theoretically gotten. I mean, if everything had gone absolutely perfectly and we didn't lose anything, that's how much we should have ended up with. How much did we actually end up with? Well, per the problem back here, we ended up with 10.0 grams. So what we've got in the problem is always less than what we should have gotten. So in order to express that as a percentage, it's always part divided by whole. So we're looking at the percent yield is what we actually got divided by what we theoretically got. Actually, I'll do that on a separate. I'm going to erase this here. Okay, so Theo, that's what we got or should have gotten, I'm sorry, 18.70 grams of sulfur. The percent yield is equal to actual divided by theoretical. That's multiplied by 100%. Actual is 10.0 grams. That was from the problem. Divided by 18.70 grams of sulfur. Multiplied by 100%. And you can see, I think it's like 53.1 or something like that. 53.4. So 53.4% was the yield. So we got a little bit more than half back what we should have, is the bottom line. Does anybody have any questions about this process? Anybody have any questions?
Can we do like another problem? I'm just trying to process it right now.
Yeah, okay. That's the thing. I think there's another one on the next page here. It's not on this one. I'm going to move ahead here a little bit, Sarah. Here we go. So this is in the same vein. Okay, what is the percent yield of H2O if 50.0 liters of NH3 gas is reacted to form 60.0 liters of gas, H2O gas at STP? So what you're looking for here is a percent yield of product, and you told this in the problem. That's more evidence that that's the product right there, because you're only ever getting a percent yield of product, and that's the H2O. What are we starting with? Well, the reactant here is NH3, and that's where we should be starting in the problem. And that should be with 50.0 liters of NH3. Sorry, NH3, I'm sorry. So looking at what we're going for, well, you see, we're looking for liters of H2O, because if you look at the product, that's what we have. We're given liters of H2O at the end. So that's what you put there as to what we're looking for. So we've got moles of moles of NH3, I keep on saying HNO3, moles of NH3, and then moles of H2O go here. And we get that from the flow chart. So start out with liters of NH3, moles of NH3, moles of H2O, and then liters of H2O. And we know it's liters because that's what we're given in the problem for the product. Anybody have any questions so far?
No.
So liters of NH3, moles of NH3, and then moles of H2O goes on the bottom down here. Then the relationships, 1 mole is 22.414 liters of NH3. The relationship between moles of H2O and moles of NH3, 4 moles of NH3, 6 moles of H2O, 6 and then 4. And then the relationship, 22.414 liters of H2O and then 1 mole of H2O. Now this one's pretty easy. You can see the math, 22.414 will cancel. You do 50 times 6 over 4, which should be about 75.0 liters of H2O, if you just do the math on it. But you know, if you wanted to, you could just plug in all the numbers. That's what you should get at the end. And that's the theoretical yield. That's what we should have gotten. Now the percent is going to be actual divided by theo times 100%. Remember, this is theo over here. The actual is given in the problem, 60.0 liters divided by 75.0 liters of water. That's times 100%. And that comes out to be 80%. 80.0%. Does anybody have any questions?
Nope.
Okay. So the secret again, always start with whatever the reactant is. So look at the two things you're starting with. So in the problem, and then look for the one that's a reactant. And it'll always be one that's a reactant, one that's a product. And the big clue here is you always ask for the percent yield of something. That something is always a product. That something is always a product, which means that whatever else is left must be the reactant. If you take that and just look at the wording, you should be fine. All right, any other questions? Okay. Okay, well, let's go back now. We'll take a look at the limiting reagent problem. Okay. So in a limiting reagent problem, you're always given two reactants. You're always comparing two reactants. And that's the first thing to realize. It's very different from a percent yield problem. So here's my classic example of a limiting reagent problem, and it's the cheese sandwich. It's a pretty boring sandwich, I must admit. It consists of two slices of bread and a slice of cheese to form a cheese sandwich. So I'm going to use this as my example to determine how many cheese sandwiches we should be getting from this process. So let's say we start off with 4 bread and 2 cheese. How many cheese sandwiches should we end up with? Anybody know? Anybody have any ideas?
Two
Two.
sandwiches?
Just 2. Yes, 2 cheese sandwiches. So the reaction here, or the process, is 2 bread plus 1 cheese gives 1 cheese sandwich. So if you've got 4 bread, 2 cheese, we get 2 cheese sandwiches. And usually no people don't have a problem with that. Now, what if we did something like this? Let's say I've got 10 bread, and now I've got 4 cheese. How many cheese sandwiches can I get now?
4.
4. Because while I've got just 4 cheese, I would need only 8 slices of bread in order to make that reaction happen. But then that means there's going to be bread left over, 2 slices to be exact. So what that means is the limiting reagent here is the cheese. It's the one that's limiting how much product we can actually get, because there's less of it. Less of it, not only numerically, but also when we take the moles into account as well. See, we need 2 breads for 1 cheese. So we'd need 8 breads for 4 cheese. We have 10, which means we have an excess of bread. The limiting reagent is cheese. Does anybody have any questions? All right, what if we had 6 bread and we'll say 4 cheese? How many cheese sandwiches can you make then?
3.
Just 3. Now, Jacques, how did you get 3?
Because you need two bread for the sandwich.
Right, so you divided the 6 by 2, didn't you? To get 3, yeah. Yeah, so that's important. I mean, you need to see that this ratio here of 2 bread to 1 cheese is of great importance to the solving of the problem. It's not about just how many there are, it's how many moles or how many breads and cheese you need to get that cheese sandwich going. Yeah, but that's exactly right. All right, so that's my explanation here as to how to deal with limiting reagent. Now, in actual chemical problems, you'll see that in this one, we're given 100.0 grams of Bi2S3 and 99.0 grams of HNO3. How do we deal with this? Well, what we do is this. The first thing we do is we convert this into moles, because moles is really the only thing we can deal with on a apples to apples, oranges to oranges basis. The relationship here is 1 mole and 514.14 grams. Then we do something that we just talked about. So we do times 1 over, in this case, 1 mole of Bi2S3. Now this will give me a number that represents what I'm calling a mole ratio. That mole ratio in this instance is 0.1945, and it doesn't have a unit because everything cancels. This isn't the last step. We need to do something else here. The other thing we need is the HNO3, and we do the same thing with that. We convert the grams we have of that into moles. Then we do times 1 mole of HNO3 over the molecular weight 63.015 grams of HNO3 times 1 over, in this case now it's 8 moles of HNO3. All right, so let's see where that comes from in a second. So we've got equals 0.1963, I think is the answer there. Yeah. All right, so let's look at where those come in at the end there. See, it's 1 mole of Bi2S3, 8 moles of HNO3. That comes from the reaction. Now, often people wonder, well, 1 watt times 1 over, what's that 1 there? 1 watt, 1 watt of something. Well, the thing is, if we're doing times 1 over something, then it's times 1 over something is equivalent to division. It's like if I said I wanted to divide by 2, that's the same as times by a half. And that 1 there is just reflective of that process. So times 1 over something is the same as dividing by it. What are we doing? We're dividing by the number of moles. It's what Jacques was doing when we were doing that last problem with the bread and the cheese. He divided the 6 by 2 to get 3, because that was the number of moles of bread, or number of bread slices needed to make 1 cheese sandwich. It's the same thing as what we're doing here. We find the number of moles and we divide by the number of moles from the reaction equation. And that's really the key there. Does anybody have any questions? Any questions? Okay. Well, let's look at wait for that to disappear. Come on. Sometimes this thing thinks it's smarter than I am. Okay. That's better.
So would the limiting reagent be Bi?
Oh, sorry, I didn't finish, did I? So what would,
You're
yeah,
good.
okay. So what is the limiting reagent?
Bi2S3?
And why'd you say that, is there?
Because it seems that it's smaller.
Right, it's got the
Then-
smaller mole ratio. So that's right, yes. That is the end of the problem. Yeah, I'm sorry about that. So LR is Bi2S3. It's the smaller of the 2 mole ratios. That's right. Thank you. All right, any other questions? Yeah, thanks for pointing that out.
No, you're good.
All right, let's take a look at what I did mean to do was expand this screen a bit and see if I can do that. It's not really giving me much. Okay, so remember that you do have a video for each of one of these assignment problems. Now the assignment here is this one is one of the longer ones. So make sure that you don't leave this one to the last minute. That's a definite. You do that, you'll be in a world of pain.
When
So
is
it's
this
a-
test?
Sorry?
I was going to ask, when was this test?
I'll tell you what,
Is it-
Joseph, let's look at that after we get done with this part, okay?
Okay.
And we'll take a look at the syllabus together, and we'll make that determination, okay? I mean, you can also tell by looking at when it's due, and I'll get to that in a second. So for this one, now remember, this is like the module 7 one I showed you the other day. You find the 1 and the 2, which is going to be some sort of moles of CO2 on top, moles of H3PO4 on the bottom, and again we've got the chemical reaction up here as well. And let's see, so it's 3 moles of CO2, 1 mole of H3PO4. Okay, so there's a lot of distractors here. 3 moles of CO2, 1 mole of H3PO4. And the rest of these are incorrect answers, so we just put 3s in each of those. And that's what you'll do for each one. Does anybody have any questions? So there's a lot of those kinds of things there. I'll show you a percent yield question as well. So this is a percent yield question. It's actually a multiple choice question, but it's pretty awful multiple choice. A lot of choices here. So this really tests your ability to determine what you've got at the beginning and what you're looking for at the end. It says here, calculate the theoretical yield if 350 grams of Na3PO4, 350 grams of Na3PO4 are formed from 692 grams of NaHCO3. If you remember what I had told you, always start with the reactant, which is the NaHCO3 here, and go to the product, which is the Na3PO4. So the Na3PO4 is the product. That's what we're looking for. So what you're going to be looking for is going to have grams of Na3PO4 at the end. And once you've done the maths, you'll find the right one there, and you'll be able to choose it. But there's a lot of other choices there, so you've got to be careful about which one you're choosing. Anybody have any questions? So this is the limiting reagent problem, and you can see here how we have to deal with that. And it's just the same method as what I had done earlier. So you would do here moles of NaHCO3 would be first, and then you divide that by 3 moles of NaHCO3. And the H3PO4, again, find moles of H3PO4 and divide by 1 mole of H3PO4. And figure out the limiting reagent by comparing 5 and 10 here. Whichever one is smaller, that's the limiting reagent. So this will be good practice for doing all of that. Okay, I wanted to go through one of these problems here at the end that kind of combines limiting reagents and let's see if I can get to it. Here we go. All right. So problems 30 through 32, these are the last ones on here. So sometimes this confuses people, so I'm going to go through this last, through problem 30 here. Oops, I didn't mean to get rid of all of that. So it's the theoretical yield of Al2O3. That's what you're looking for first. So let's look at the problem. Actually, I'll move it back here a bit. There we go. How many grams of Al2O3 could be produced from 225 grams of Al reacting with 300 liters of O2? How do you deal with that? So one thing you have to realize is that if you've got, this is what you're starting with, is the Al and the O2. Those are both reactants. And when you do these kinds of problems, this is another way of being able to determine limiting reagent, by the way, is we can start out with 225 grams of Al, and we can ask ourselves, well, how many grams of Al2O3? So we can get this theoretical yield here. And the other one is the 300 liters. And we ask ourselves how many grams of Al2O3 we're getting from that. By the way, this is also in the soft chalk too. I didn't show you these problems, but they're there as well if you want to look at them. But whichever one is smaller, that's a limiting reagent. So let me give you another example with the cheese sandwich. If you remember, it's 2 bread plus 1 cheese gives 1 cheese sandwich. So again, if I started out with 10 bread, that should create 5 cheese sandwiches. But if I start out with 6 cheese, that would give me 6 cheese sandwiches. But the smaller one is the 5, which means bread is limiting. Does anybody have any questions about just that cheese sandwich analogy that I'm doing there? Okay. So 5 is smaller than 6. That's how I know bread is limiting there. So we do the same thing here with this one. And to get the theoretical yield of aluminum, you can see it's that same process as we did earlier. We're looking for grams of Al2O3 at the end. How do I know that? Because that's what we're looking for. It says how many grams of Al2O3. So that's the theoretical yield we're looking for. It'll be moles of Al on top, just following the flowchart. Moles of Al2O3 here, and then grams of Al, moles of Al, and then moles of Al2O3. 1 mole of Al, 20, what is it, 26.98, yeah. And then the moles of Al2O3 to moles of Al, look at the reaction. We've got 4 moles of Al forming 2 moles of Al2O3, 2 and then 4. And then the number of grams of Al2O3, 101.96. And then that's 1 mole down there. That's going to give me a certain amount of aluminum. Let me see what it's going to give. I can't remember off the top of my head. It would be it'd be about 400 and let's see. I think it's. So somebody want to do the math for me? I think it's 544, but I'm not 100% sure. Or it's 425, something like that.
425.
425, thank you. So it's 425 grams of Al2O3. And the other one, we start off with 300 liters of O2. end, we're going to end up with, let's see, moles of O2 on top here, moles of Al2O3 again, and we're looking for grams of Al2O3. And on the bottom here, liters of O2, moles of O2, and moles of Al2O3. Now the relationship there is 1 mole, 22.414 liters. Let's see, the relationship between moles of Al2O3 and moles of O2. Go back up here, you've got 2 moles of Al2O3, 3 moles of O2. So that's from the reaction, 2 and 3. And then the same molecular weight, 101.96 grams of Al2O3, 1 mole. Okay, let's see, do I have a little bit more room on the bottom here? No, I don't. Okay. So the answer here for that is going to, can someone give me the math on this one? 300, in your calculator, you could put 300 times 2 times 101.96 divided by 22.414 divided by 3.
909.7. So would that go to 910?
Yeah, let's go 910. That's good. 910 dot. 910 dot grams of Al2O3. So you're asking yourself, well, which one is the limiting reagent? Well, it's the one that gives the smaller amount of Al2O3, which is going to be the aluminum. So the aluminum is limiting, and the amount of grams of Al2O3 we'd get would be 425. We can only get the least amount, not the most amount from this. 300 liters of O2 would have given 910 grams if we had enough aluminum in order to react with it, but we don't. So aluminum is the limiting reagent. Does anybody have any questions?
So aluminum is the limiting reagent?
Yes, that's right. But the
Because it's
theoretical,
425.
right? But the theoretical yield of Al2O3 from 225 grams is 425 grams of Al2O3. The theoretical yield of Al2O3 from 300 liters of O2 is 910 grams. The limiting reagent is Al.
Okay, thank you.
All right, so you'll see that again. I do have this, these kinds of problems in the soft chalk. I'll show you where they are if you want to take a look at them. Yeah. It's page 10. Here we go. So this is an example of that kind of problem. So on example 12 is lays out how to handle that problem and how to get the 2 theoretical yields. So that this is also in module 9 as well. And there's another example. I think it might be example 9. Oh, example 10. And I guess that's it. All right. So that's that's one you can look at in order to get some more guidance on doing those kinds of problems. Now that's the That's the assignment. As I said, there are videos for every last one of those assignment problems. So if you have any problems again, go look at the video for that. And that'll be helpful to you. Oops, didn't mean to do that. So you can see the way that the practice quiz and the credit quiz is set up is just what we had talked about earlier with the like module 3 or even module 7, just typing in each of the different things into the boxes, numbers, units, compounds. For the percent yields, that's a little bit different. You're looking for a theoretical yield. Now you can look at something like this and it says expressed with unit and compound, for example, grams of Zn. Well, obviously zinc isn't one of the reactants here. It's telling you that you need to express whatever unit you're looking for along with whatever compound you have to be looking for from the problem. For example, in this one, we're looking for the percent yield of HBr, which is the product here. So the final answer here should be in grams of HBr. So grams of HBr, what the GHBr would be what you would put here for the theoretical yield unit. And the percent yield, of course, will be a percentage. And that's what it says here, express as percent. Does anybody have any questions about anything here in module 9?
Nope.
All right, well, you've got your work cut out for you. Module 7, 8, and 9, you should be able to do the homework on. I strongly, strongly recommend doing them soon and not leaving them till the last minute. I keep on saying that, but most people, I don't know what it is. Most people just tend to leave it till the last day. I don't understand it, but anyways, they do. If anybody wants to give me any insight, maybe via email, you can tell me, you know, why things get left to the last day. That might be helpful. It might give me some perspective, but I can't understand it. It's not what I would have done as a student. It's not what I ever did as a student. So I don't know. But it seems like 80% of people like to leave things till the day that they're due. And I don't understand it. I can't wrap my head around it. But if anybody wants to help me out with that, that'd be great. All right. Okay, I guess we'll leave it there for today. And I will see you all on Wednesday. Thanks for coming.
Thank you,
Professor.
Professor.
Thank you.
All right, thanks everybody.
Thanks, Professor.
See you
Have
all
a nice
later.
week.
Thank you, Professor.
Zachary, did you want to hang around? Oh, he's already gone. Abram, did you need me?
Hello, Professor. I just have a question. If I
Yeah.
can use that calculator for test 2,
Yeah, if you can use it.
I can use it. Do you have any specific required calculator like TI's?
Well, show me the one you want to use.
I'm using this
That's okay.
TI-84. It's okay.
Yeah, that's right.
Okay.
Hey, Zachary.
Thank you,
I'll
Professor.
talk. Yeah, just wait a second. I'll talk to you.
No problem.
All right. So Abram, is there? Yeah, that's fine. That's okay. You can use that one.
Okay. Thank you, Professor.
All
I'll
right.
see you later.
All right. Bye-bye. Thanks, Zachary. I'm glad I caught you. So I actually haven't read your email that you got back to me yet. I mean, I did read the one you sent earlier. You there?
Yes. So I sent an email back just regarding basically the lab work, because mainly in this class I watched the recording and I was able to attend today. The lab course I wasn't able to get through our
hang on.
classwork.
Let me
Sorry.
finish something here. I need to stop the recording because we don't need to have this